Hello, Anne. Thank you for your email earlier. I really enjoyed reading through this. I love Fresh Air. I love Terry Gross. My buddy back in Philadelphia works for Terry, so it's pretty rad seeing this come across my email inbox today. I started typing you up an answer, and I realized it's probably actually easier to just send you a video explaining some stuff. So I loved reading through, and I saw the quote that this physicist, Brian Greene, said, if you shuffle that deck, there's just so many orderings that can happen. And we know that's correct, 52 factorial of them. We figured that out in class last time. If you shuffle that deck enough times, the orders will have to repeat. Okay, that's not true. It's likely that eventually something will repeat, but they don't have to repeat. And I'd like to put some math to that today with this. Now, what I want to do is, I'm going to come back to this in a second. I started building you a spreadsheet. Give me 1 second to get it ready here. And I'm going to start with something easier than a deck of cards. We're going to start with a single six-sided die. Now, a single six-sided die, if you... Hang on 1 second. I'm going to close my email for just a sec so I stop having people pop up with their notes in the video. If you start with a six-sided die, I'm going to have Excel roll the six-sided die as many times as it takes until the die repeats a side. So for example, right here, this is where the rolls are happening. Excel rolled a 2, and then a 1, and then a 1. So it took 3 rolls until we got a repeat. So this is 3 rolls until we got a repeat. There's what just happened, and it's keeping track of it right here. I'm going to roll again. This time it only took 2. It rolled a 6, then it rolled a 6 again. In case you're wondering where these rolls are happening, I've got them hidden up here, and they're called RAND between commands. And we will deal, we'll deal with these later in class, I promise. We're getting a little ahead of ourselves here, but your question is so good. Okay, now I'm going to roll again. Okay, that roll took 4 rolls because the dice went 4, 2, 3, 4. The repeat doesn't have to happen right next to each other. It can just, that's not what the physicist said. The physicist said eventually one of the orders is going to show up again. He didn't say right after the other. He just said it's going to show up somewhere. Okay, so this one took 5, 3, 4, 2, 6, 3. This one took 2, 4, 4. This one took, again, 2, went 2 and 2. You might notice the most it can take is 7. I'm going to see if I can get one of those really quickly. I usually can't because it's pretty rare. It's about 1 in 100 to get a 7. I'm not going to get one right now, and that's totally fine. But what you're seeing is, you're seeing that there definitely is kind of a normal area that the experiment rolls into. No pun intended. So what I'm going to do is I'm going to grab my little stapler here, and I'm going to hold down the F9 button. Nope, a 7 just happened, and I missed it. It went by really quickly. So what you can look at is, you can look at the total number of rolls it takes until you get a repeat. The least is 2. It might happen in 2, and it might happen in 7, but it can't take more than 7. It cannot take more than 7 rolls until it happens. Okay. You can look at this mathematically as well, not just. This is a Monte Carlo simulation, just I'm sure you know because you've seen them. It's keeping track of the data, and we can actually, I ran a little average here while it's calculating up here. It's running an average, and it takes about, on average, 4 rolls until you get a repeat. So that's in this experiment, it appears to be 3 and 4 appear to be almost the most common, and the tipping point or the balancing point is 4. So we're going to talk more about all this as the class goes on, I promise, within week 5, week 6, somewhere in there. Okay, I'm going to stop that for a sec. Another way of looking at this is looking at a six-sided die and keeping track. I'm going to actually white this out for a second and come back to it. Looking at a six-sided die and rolling it, and the chance of never seeing one of the sides. So in other words, the physicist said, eventually if you roll enough, you'll get a repeat somewhere. The opposite of that is that you might roll and never get something. There might be something you never get. So this is the math, and I'm not going to get too far into the math right now because we'll get into this later in the course. If you roll a six-sided die, then the chance of not getting a certain side is 5/6, because there are 6 sides and 5 of them are not that 3. So if you roll a die 1 time, it's 5 out of 6. And this is the math that gets a little bit headier for class right now. If you roll it twice, it's 5/6 squared. If you roll it 3 times, it's 5/6 cubed. 4 times is 5/6 to the 4th, and so forth, and it drags it all the way down. Don't worry about that math right now. We'll learn it in this class, I promise. What this means, though, since this is an exponentially decaying model, is the more you roll the die, the less and less likely it is that you never see a 3. That's what the physicist is getting at. He says if you keep dealing out the decks, it's less and less likely that you won't get something to repeat somewhere, because it becomes almost impossible to have something never show up. See these zeros that are down here? These aren't really zeros. They're rounding to zeros. That's 0.2%. And even down here, whatever is 100, the 100's not 0. It's whatever the heck that is, 0.000001%. So that's 1 in 100 million or so. Okay, so what the physicist is getting, this is his mathematical point. He says if you keep quote unquote dealing the deck, or quote unquote rolling the die, eventually the chance of one of the outcomes never happening goes to 0. So the chance of all the outcomes happening eventually becomes 100%. This is just the other chance. If there's an 83% chance of never seeing a 3, there's got to be a 17% chance of seeing a 3 somewhere. And you'll notice as these go down, these go up because they have to add to 100%. Okay, that's great. That's a 6-sided die. But a 6-sided die is completely within the realm of the possibility of what we can perceive, because these numbers aren't very big. They're doable. They're mentally doable. Okay, so I started trying to build this spreadsheet in Excel, and I realized something pretty quickly. Excel can't handle these numbers. There's no way Excel can handle these numbers. Sorry about this. I increased the decimal so many times when I was goofing around with it. Oh, heck, I'll make it. I use the same math. Here, I'm going to delete all this stuff out here so you don't have to look at it. Delete. Okay. What I did was I repeated, remember this formula over here? 5/6. 5 divided by 6. I figured, well, 5 divided by 6, that's 6 is the number of sides on the die, and 5 is the number of sides that aren't a 3. Well, I figured, okay, let's make a die that is 52 factorially sided. This is going to sound crazy, but you can envision all the numbers of ways to deal out a card as sides of a die. And that die would have 52 factorial sides. So it would have 8.1 times 10 to the 67 sides. All of those sides would go into the denominator of the fraction, just like 6 went into the denominator, over here, 6 went into the denominator of this fraction. And the numerator of this fraction is 1 less than 6. So the numerator of this fraction, I don't know what I just hit. I'm going to hit escape. I'm hitting too many buttons. The numerator of this fraction is 1 less than 52 factorial. And then I pressed enter. And the problem is when I pressed enter, the thing tells me it's 100%. Now you know it can't be 100%. It can't be, because you're dividing a smaller number by a bigger number. This has to be like 99.99 something. But Excel can't handle it. As a matter of fact, that's what I was doing before. I was trying to increase the decimals until I got some 9s, and guess what? It can't. It just can't handle them. So I decided to move to my good buddy, the big number calculator. This one seems to help me out a little bit. So what I did with this one was I re-put 52 factorial in. This is one of the ways you can get all the digits of 52 factorial. And I decided to try to use the big number calculator then to analyze this expression right here, 52 factorial minus 1 over 52 factorial. And because this calculator exists, I was able, excuse me, to actually, here's 52 factorial, and here's 52 factorial, take away 1. Take away 1. And then I hit divide, and I came up with this beautiful number up here. As a matter of fact, I haven't tested it. I wonder if I can get some more decimals. Oh my goodness. Oh my goodness, I can get tons of decimals. I can get, this is like, I'm like a kid in a candy store right now. Look at these, this is ridiculous. So remember I said it should be 99.999 something? Well, there it is right there. It's right there. That's the chance. If you deal out a deck of cards and then deal them again, that you will not get, excuse me, if you deal out a deck of cards, oh my God, this is even hard to say because the numbers are so big. Imagine the 52 factorially sided die. One of those sides is 3. This is the chance that you don't roll 3 on a 52 factorially sided die. Now, with a 6-sided die, it was a normal number like 83%. For a 52 factorial sided die, it's this massive thing. I wonder if I can copy this into Excel. Oh my God, and if I can do this. Oh no, oh no, Excel still can't handle it. Oh, yes it can. Well, it can kind of handle it. You see the problem? It can only handle it to a point. It can't handle it. It can't handle it past that decimal point. That's its floating point problem. But I have another idea. We can redo what I want to do Excel by copying this into back into the big number calculator and raising it to powers. That's the chance. I give myself 500 decimals again. Uh-oh, that's not right. There we go. That's the chance if I roll the 52 factorial die 2 times, I will never get a 3. If you look at that number, you might look at that number and go, that's the same as the other number, but it's not. It's not. They're different. This one is a little bit bigger than that one. You can see it right here. You see how that part of the number is 8760 and this part of the number is 7520? It just got smaller. If I roll it 3 times, there's the chance. It just got smaller again. If I roll it 4 times, there's the chance. It just got smaller again. Now, with a 6-sided die, after I rolled it, about 30 times, there's almost no chance you're not going to see a 3. But when you have so many sides, I'm over here now, I'm going to close this one. When you have so many sides, even rolling it 30 times really doesn't put a dent into this number. We're still at 99.999999999. Let me zoom out a little bit so I can see everything at once. Here we go. As a matter of fact, I can roll it 1,000,000 times. And it's still, oh no! Oh well, crud. I was hoping we could use this. I think we just found the limits. Can we do 1,000 at least? Nope. Maybe, hang on. Let me limit the number of digits. I'm trying to find a way to make this work. Nope, it's not going to like it. Maybe we can just do 20. Okay, it doesn't mind. Wait a minute. Oh, it was thinking. It was okay with 500. It had to think about it a little bit. Okay, let's try 10,000. Hang on, Ann. It's thinking. Oh my God, I got impatient. I can't believe I got impatient with this. It's thinking about it. Oh my God, oh my God, oh my God. It's thinking, it's trying. We're actually, this is incredible that we have created a number that's so big, it's taxing modern computing technology. This goes to show you how insane this is. So what I'm going to do, Ann, I'm going to end this video now, and because I don't know how long this is going to take. Yep, fatal error, maximum execution time of 37. Oh God. Well, I think, even though we just got an error, I believe we have gotten a response to our physicist buddy here. If you shuffle that deck enough times, the fatal error is that enough times is multiple times longer than the universe has been in existence. And I think that's the idea of these big numbers, and why when he says if you shuffle that deck enough times, the orders will have to repeat. That is a kind of overly simplistic statement. It's true. It's mathematically true. It's just not practically achievable. And as I come up on a 15-minute long video, Ann, I'm sorry, but I wanted to get you an answer to this because I loved your question. So I'm going to go ahead and put this on YouTube and send it to you, and I will see you soon. Feel free to send me any emails with any more awesome points. Be well, my friend. Have a great weekend.